A guy in the Netherlands figured out that Coinbase wasn't handling wallet transactions correctly. So they noticed that they sent a transaction to a Coinbase wallet, but in the transaction they did a revert at the end. But Coinbase, and this is where we just have to assume, how was Coinbase doing this? They must have been reading logs or looking at transactions and not realizing, and they wanted to get the results to the user as soon as possible, right? And so they were parsing the logs, you could imagine, and then they didn't really parse the part that said, oh, never mind, this transaction shouldn't have even happened. So the guy noticed, hey, I sent a transaction and they credited me money, and if I do this again and again and again, they're just crediting me more and more money. So what did he do? He was ethical. He reported it to Coinbase. He got a bug bounty of $10,000 instead of taking all the ETH that Coinbase had on hand, which is like a lot of ETH. So we're going to share these slides, and there's a link to that article in the back. It's kind of called the Christmas attack from last year. But those kinds of things got me interested in the space. I was in software security. You could say a side effect of all these things is maybe it's gotten some of you or some of the security people in the room over to this ecosystem, because like these are heists. You know, this is a lot of money that we're talking about. In this case, it was only a little bit at a time. But if you're an exchange and you're managing a lot of money, you better make sure your contract or your transaction handling code is pretty good. So that was 2017, and then Scott's going to talk about some of the fun things that we've been talking about in 2018.
Awesome. Hey, my name is Scott Bigelow. I'm a blockchain engineer for Augur. I've been there for about a year, in this space for about 2 years. And in that time, I've had an opportunity to see a lot of interesting Solidity hacks and reviews of contracts that came back with some interesting stuff. So these are some of the most interesting things that I found that I wanted to share. And I've given them each terrible names just so it's really easy to go between them, because sometimes they're really related. So this one I'm going to call the extravagant miner. And similar to that last talk we just had, where they talked a bit about the importance of bug bounties, Augur, before we released contracts to the Ethereum, or before they were released, we ran a HackerOne bounty, where we gave everybody the set of contracts, and we said that here's kind of a high-level description of how the incentive system in Augur is supposed to work. What was interesting is that somebody read the high-level description of how Augur was supposed to work, didn't even look at the code, and filed a bug bounty. Because what they realized is that, well, I'm going to tell you a little about Augur. When you use Augur, you create a market. And as part of creating that market, you say, is the weather going to be over 60 degrees tomorrow? You are creating an obligation that you are going to come back and say what the result of that was. And there's no way to really make somebody do something in Ethereum. We make them post a bond. And this bond might be 0.01 ETH. But let's say gas prices in a year from now are extremely high, and 0.01 ETH isn't enough to incentivize that person to come back. Or isn't enough to incentivize the person who ends up reporting on it, who gets this bond, to come back and do it, because they're going to spend 1 ETH in gas to get a 0.01. So we need to kind of figure out what these gas prices are in the future. The way we did that is keeping like a rolling average of what gas prices were whenever regular reports happen. If you have hundreds of reports in the last month, you can kind of figure out, everybody uses about 4 gwei, so we'll adjust the bond size based on this gas price. That seems like a pretty reasonable approach, right? Here's the problem. Here's a simple screenshot from Etherscan. The fees over here that are paid per transaction and the fees that a miner receives are equal. So a miner that wants to report on a market can use an extremely high gas price. Imagine they put 2 million gwei in there. They pay 10,000 ETH to submit these initial reports. They can completely jack this bond size. They can make it cost 40 ETH to create a market by pretending to pay so much in gas. Now, they're going to get it back, but because they executed this code and their gas price was, say, 2 million, they're going to influence the system to make this bond size too large. So here's the code. The code itself isn't that interesting, but what is interesting is if you run unit tests against this, right? This is very, very well tested code, but we were testing the wrong thing. We didn't consider some of the ways that Ethereum works that could make this strategy, aside from the fact that the code works great, make this strategy not a good strategy. So here's another one. We call this one the diabolical airdrop. So similarly, when you create a market, you need to put a bond up there. You also need to put rep. Like a small amount of rep needs to live on the market. And so when we're creating this market, it's a brand new contract. we create it and we end up forwarding along some rep. And we say, hey, make sure that the amount of rep on this is equal to the amount that you're supposed to have on a market. Only happens at initialization. So we need to talk a little bit about how the system works really quick. I've got some sweet diagrams here. So we have a market factory that has an address, and you can send a transaction to it with some rep, and it goes ahead and it says, oh, I will create a new contract, and I will run that code and make sure that 1 rep equals 1 rep. You notice this is 0x5678. Let's take a step back, pretend this didn't happen yet. Pretend some jerk figures out what that next contract address is going to be and moves the teeniest portion of a rep to this address, right? Because of the way Ethereum works, accounts and contracts share the same state, the same space, and you know deterministically what those new contract addresses are going to be, you can move a little ether there before. So now when you come along, try to create that market, that equality fails. That equality was there to make sure that things didn't go wrong and made something go wrong. So I think this also comes down to understanding that this isn't really like a safe space, right? Ethereum is not this clean space. There's all sorts of things that you need to understand, like the fact that that newly deployed contract, that might not be the first time that address has been manipulated in the network. This one's called, I thought I was done with pointer hacks since I stopped programming C like 15 years ago. And I was really grateful for Elena's talk yesterday. I don't know if you saw that about storage slots, because we're going to talk about storage slots, and I don't need to go over that because that was a great talk. But this here is a honeypot. This is a contract that somebody deploys where they try to have people who know something about Solidity look at it and say, you know what, I understand how this contract works, and I'm going to take all of their money, but they're going to take your money. And this code looks, this code looks pretty good. And it was kind of a small screen, kind of hard to see. But to talk about what's happening here, basically we have a play function. You pass in a number. If you guess the secret number, which is just sitting there in storage, and you get it right, they will send you all the ether on that contract. Here's the problem. Based on the storage slot talk from yesterday, we have storage slot 0 and storage slot 1. But there's also an implied storage there on that struct game. And because it's not set to an existing storage item like you would have gotten out of a mapping or an array, it just defaults to offset 0. And so the impact of that is that storage slot 0 is being overwritten in that line, and storage slot 1 in the next.
Wait, why?
Because that is a kind of an improper way to initialize a struct. You didn't initialize a memory version of a struct. You initialized an uninitialized storage pointer starting at offset 0. Really what you should have said here is game memory game, or game and then point to some existing bit of storage stripped out from an array. And Solidity knows that this is messed up. Solidity knows there's a big problem here. But you know what doesn't know that there's a big problem here? When you go to Etherscan and you look at this contract, which is the way that I think a lot of people who likely interact with a contract look, there's the code. This is a real honeypot. People made money. And there's no warnings here. Like that Solidity warning is extremely valuable. So when you plan on interacting with these things, don't use some weird centralized thing. Bring these things into Truffle, play with them, compile them. Don't just leave it to, oh, that's how the code works. Let's go ahead and ship it. You're going to end up losing your 0.1 ETH.
What does the transaction history look like?
Go see it. Bunch of suckers. Yep. And okay, I'll tell you this because I really like this. The really cool part about this, if you look at the actual code, this is the stuff, is that the way that they overwrite storage slot, the way that they initialize storage slot 1, which was last played, that ends up getting overwritten by the number that you guessed, which was had to be under 16, which means that they can always call kill on this because last played was plus 1 day. They're constantly inserting basically a Unix time of 16 or less, so that kill can always be called by the owner, even if the game was just played a minute ago. Sorry, that wasn't. Only because you asked about the transaction history. Okay, going back. this one I call, there can only be one 0xF3 return opcode, honeypot. This one's cool.
How do you figure something like that out?
I think, I'll tell you how I did.
The person that originally made that
Yeah.
has to understand pointers so well. Like, they could make so much more money doing actual security.
You know, and maybe they are. Maybe this is like a little pet project. You know, hey, I want to make 0.8 ETH on the side. But I imagine they probably ran into it on accident. They're like, oh my god, I can totally burn somebody with this.
Wait a minute, just to that point for a second, like, back in the day, people used to put out hacks just for notoriety. Like, they just wanted to get their hacker name out there. Like, then people started being, you know, security auditors and having that be a career. But here, you have just direct money on the internet flowing around. So it's a whole new world, a new evolution.
So we need to talk about what it's like when you actually deploy a contract before we actually start about how to structure this hack. So when we write a contract, we generally think, okay, I'm going to write this contract, it's got a constructor, it's got the rest of the contract in it. I'm going to take this, put it into Ethereum, and it calls the constructor. And that's not how it works. So I moved that big section down here to the left. This is more akin to what happens. So it basically pulls out the constructor into like an EVM script, and then it returns the rest of the contract, right? So there's a level of indirection there. You don't deploy the constructor, you run it first, and then the script that you give it returns the actual body of the contract that's going to live that contract address. And of course, this is Ethereum, so it looks more like this, right? Does some EVM stuff where it sets the constructor stuff, and then it returns the hex code that's going to represent that EVM. So here's the hack. Let's say you walk up to this contract, it's got 2 ETH on it, and you just look at it, there's a withdraw function there. It doesn't even talk about any storage state on the thing. You'd say, hey, this withdraw function, if I send it 1 or more ETH, it sends me everything. I'm gonna go ahead and send it 1 ETH with a withdrawal. The problem is what happened in the constructor. There's an assembly return here, right? And so there's like, okay, this thing has an identifier, I guess it's running an identifier or something. It kind of looks, maybe you can call it owner and it looks pretty good. But what's actually happening here is that you are subverting the real return of the contract bytecode that's going to live at that address and returning your own raw in that constructor. So you can kind of think about this, right? There's only one return. When you return from a function, you're done. So even though that contract has all this other stuff in it, it doesn't matter. You are returning something else in the constructor, and none of that code actually lives there. And the hack is actually in that bytecode. If you send the right thing here, somebody else can withdraw all of the funds there, and it's encoded in EVM. Call this one, I am not a robot. There are many legitimate reasons for a contract to say that a contract cannot interact with you. You know, if you're running some sort of a game that has like a randomization or a lottery based on like a block hash, a contract could figure out the right answer and submit that transaction right away. So a common way that this was done before was to simply ask the EVM, how much code lives at this address? And is that 0? If that is 0, well then obviously it's not a contract. And if it is more than 0, then it's a contract. So let's pretend this function is going to send 0.1 ETH to anybody who's not a contract that calls this function. Let's go back about, and cover what we learned about how constructors and returning contract code works. And we write a contract that's going to abuse this other contract. And all that we do is make sure that we interact with it in the constructor. If we go back and look at what we learned here about, I don't know if you guys can see this, it's kind of a small screen, but if we do this, if we interact with it in the constructor, we haven't returned the code for it to even look at the size of it, right? The code doesn't live there yet. You haven't returned what actually gets specified. And so when it comes over here, at the time that it's being invoked, that code size is 0, therefore it's not a contract, but you can still implement the full EVM inside of your constructor and do all the nasty things. And so the real way to fix this problem isn't to look at the code size, is to inspect the tx.origin, which is your sending address, and the message sender, the thing that is interacting with the contract, and make sure that those two things exist. We don't know of a way yet to break this, but I'm looking forward to it. Yeah, and that's the end of my section.
Just doing one more to kind of bring it back home. Those were a lot of the things we saw this year in Solidity. And this I kind of referred to as an oldie but a goodie. I used to teach some secure coding classes, and we'll see if there's people in the room that get this one. It was really nice to see a lot of ahas in the audience in the last few examples. I don't know if you can see that, so let me zoom in a bit.
Sorry, we expected a screen the size of the one we were looking at in the conference hall.
Okay, so we have an example contract. It has an event called what? And there's a mapping of who has called this before. So we'll only let every address call it once at most. And it's just trying to implement a simple voting process, but instead of everybody getting, yay or nay, we're going to say, well, you can vote with some level of confidence. I've taken a lot of multiple choice tests in my life, and I get, +3, +1, +2, like strongly agree, strongly disagree, agree, etc. So that's what we're going to try to implement here in a somewhat flawed way. So it's called vote with confidence. It takes an int. We'll call that val. First thing we do is check our map. Has this address, or has the sender sent us anything yet? We keep that in a bool mapping. So only allow the next case if they haven't called it yet, and then otherwise set that to true. And we just said a negative value means a vote against. So we have a Boolean called for, and if the value is less than 0, we're going to say, well, it's actually a vote against. And then take the unary negation of val, so val equals negative val. Then we do some range checking to say, well, we're only allowing values that are less than 3, like if you think of the absolute value of the value passed in. Votes for and votes against were both UN 256s. So if it was a vote for, and we've passed our range checking, then increment votes for, and if it was against, then votes against. And then we just had that event we're going to emit if we've exceeded 1 billion votes. So just let the UI know about that. That's kind of a noteworthy thing. And return true. Otherwise, if we didn't pass all the range checking, or if somebody tried to vote twice, return false. So besides maybe Bernard in the audience, does anybody see what might have gone wrong? And besides Scott in the audience, anybody see what might have gone wrong in this contract design? Evans in the back.
You could have a really, really low negative number and like maybe a size or assigned int problem.
Is there a signed int problem?
Equal to 3, it could be negative, 50 billion or whatever.
Okay, negative 50 billion is the answer. Anybody agree with that? Huge negative number. I see a nod here. Or maybe if some people have been burned before in their career with these things. Let's look at this in particular. So val here is an int. If val is less than 0, val equals negative val. So doesn't that take the absolute value of that number? Make it positive? Someone said no. Okay. How do we? This one is kind of fun because when you're working in signed 256-bit integers, it takes like 2 minutes to pronounce the number that you have to pass in. There's only one number you can pass in to script this contract. And it's negative 57 quadrillion, and you can read the rest of it. And that's kind of my favorite number of the day. The problem here is that we're not really range checking here, because if you pass in this number, which is that number in hex, starting with an 8 and zeros all the way down, if it was a signed 8-bit, it would just be hex 80000. Turns out that's the one number in 2's complement binary math that when you take the absolute value of it, you get the same number back. That also happens with 0, but it's the only negative value that happens with. It just blew the bonus question for everyone. So at the risk of giving you guys new material with which to go out and create your own new honeypots, we thought we'd give you some tips on how Ethereum works and what to look out for. So The EVM can seem like a safe space, right? There's no servers to compromise. You just submit this code to the world computer and things just happen to work. Well, that's great, but there's some trade-offs. Part of it is due to the way Solidity works. In the pre-sharding era, nothing happens really simultaneously. So you don't have to think about race conditions. When your code is running, your code is running. But before your code is running, what did you do? You submit a transaction to the mempool. Other people can see that. If that was a bid, someone can front run you, right? And Scott also presented another mining hack. If a miner is your attacker, then you have to change how you're thinking about your adversary as well. Scalability is also going to be a problem related to the way that you go read logs. We had that Coinbase example. Well, how are they going to read logs? They have to read from every shard in Jasper? Like, how's that going to work? We don't know yet. That's probably going to be the 2019, 2020 version of this talk. We'll see. And then your code is running in the EVM, but other people can call your code, right? And you have to think about all the different ways in which other people can call your code. Part of that's during constructors. Part of that's calling public functions in libraries that aren't really libraries, that are just contracts. So, some suggestions from us. Study the best practice docs. The underhanded Solidity contest from last year is a wonderful example of people writing code that looks kind of benign, but under the surface there's lurking these vulnerabilities that are there. Honeypots are examples of that. Compile the code, look at it, but for the love of God, don't send ETH to it. And that kind of goes true for almost any contract. The consensus team called Panvala is actually developing a badging system to show you in certain UIs that this contract has been audited by security auditors, and it's probably safer than your regular contract out there that might be a honeypot. Definitely compile code and make sure it compiles without warnings, because your compiler will tell you interesting things. As Scott showed, there are static and dynamic testing tools. Maru, Harvey, and Mithril++ are some ones that were presented yesterday by Tom and Bernard from the Consensus Diligence team, and I recommend those. You have to write comprehensive tests and build that into your testing process. We've seen a lot of that. We've seen some good talks on testing at this conference as well, but you kind of have to know exactly what else to test for, so maybe your tests could be a little more comprehensive. We also see some good talks at this conference on upgradability and just kind of planning for some kind of event where you need to fix a bug, or planning for an event where you just need to freeze your contracts and don't let anything happen. And only the owner can do that. Those are nice things to have in there. That's kind of called the circuit breaker pattern. Hire auditors that are doing this stuff 24/7, and you always have an implicit bug bounty on your code when you're managing money, right? Because an attacker can just go in there and grab it. So why not put an explicit bug bounty on there and try to get those nice people, like the guy in the Netherlands, to maybe give him 10 grand instead of all of your ether, right? And then just continually monitor and learn the space. We hope we made this kind of fun for you. Here are some references. This is the consensus best practices. There's also hot off the press a smart contract weakness classification system. There is a similar thing in like regular C code. Here's something for smart contracts. There's a couple dozen examples of this is the anti-pattern. This is what it looks like in code. This is how tools should report it if you're working in this ecosystem. And it's a proposal at this point, and if you can contribute to it, that would be great too. I'm going to put up the signed integer thing I just presented to you, because I don't think that's in there yet. And I'll do that later today. And thank you. Any questions?
So a lot of people recommend not using like delegate call or assembly code, but like for like upgradable like proxy contracts, do you use that? Is that a risk? Or?
Yeah, the question is about, you can see advice that says don't use delegate call, or advice that says don't use assembly, right? And there is community debate over this. I personally kind of like the proxy contract, paradigm or method. I like it. It would be nice if the Ethereum community would just kind of settle on one kind of blessed version of it, and then all the tools know about that and say, well, that's this, so that's cool. But otherwise, you're going to see honeypots that try to look like they're implementing that. There's obviously problems with slots and memory there. You have to take care of it one way or the other. I kind of like the functionality. I guess the question also gets into You know, what about Viper? What about LLL? Or what if I'm writing directly? Just I like writing in EVM, you know, bytecode. So you'll hear different opinions on that. For delegate call, I happen to like the proxy pattern for the case of upgradability myself, and I'm sure others will disagree with me. And if they make compelling arguments, I'll listen to them. Or if the Solidity team or some other mechanism comes along that's a little more blessed in the language with less danger around it, then I would avoid using it. There's similar issues on C, for example. There's some C calls that you just can't make securely. You can always have a buffer overflow. So most people have stopped using those. And there are safer versions of code, but they take a little bit more time at runtime. In this case, they might take a little more gas. So you have to make these trade-offs as an engineer. I don't know if you have any thoughts on that.
I think it just comes down to how much you need your code looked into and like the level of audit that you need. So if you're using assembly and you're using delegate calls, you're probably going to need to open your wallet up and pay some of these auditors a lot of money, because it's going to take a lot for somebody to really trust a contract that uses these very dangerous constructs.
So the proxy pattern that I presented on main stage got security reviewed, and that included the improved functionality. So it's audited by DAPSIS.
Oh, DevSys, very nice.
Yeah.
Thanks, Linda. There's also another aspect of this, in which is, let's say you're about to call into a contract system and you trust it and it's been audited and it seems to work great, but they upgrade it later, right? At some point in the future, they upgrade it. So now you're calling into essentially untrusted code. Right? Or who's going to inherit that project in the future? You don't know. So it's always based on trust, right? And I don't want to tell contracts don't have an upgradability plan, because so it's kind of one or the other, you know. And it's a debate. I was told by the Trail of Bits guy that they're going to have an update to their cliffhanger Medium post from last week that says everybody else's upgrade plan sucks, and now we're gonna have our own. But I don't know what that is yet. He's not here. I don't think so.
Ask, but I'm not going to ruin it. It's just something simple. I think people overcomplicate it because they see the proxy pattern and say, "Oh, that looks cool. I'll just adopt that." And that's why I mentioned them on main stage at the end of my presentation, because people do overcomplicate, and I think that they're giving away a lot of there's much easier ways to do upgrades. You don't necessarily have to go with the proxy pattern because it looks cool. So you can simply move your storage across, and that's perfectly fine. If you're happy with mutable addresses and paying for storage transfer from one contract to another. Install your new functionality, move the storage across, and fine.
Yeah, you could say that pure security guys would probably like that better, right?
That's why Trail of Bits, because they need to audit all of these proxy patterns that we all want in different ways. They're like, keep it simple, guys.
Any other questions? We'll be around.